All right, this video is all about hypothesis testing. Hypothesis testing is a concept that we've alluded to in previous videos, but we haven't really come out and defined it explicitly. And that's what we're going to do in this video. We're going to take a look at a lot of examples. Now, sort of the math behind hypothesis testing is nothing new. Hypothesis testing is an important part of sampling, but what it really is it's almost procedural in nature. In other words, we're not going to be dealing with any new tables or anything like that when we're talking about hypothesis testing. Rather, we're just working hard to define the things that we're working with. And so let's start off. One of the most important parts of hypothesis testing is defining a null hypothesis and an alternate hypothesis. And the null hypothesis is our default. And you could say it's sort of the assumed proposition. And the alternate hypothesis is the thing that we're sort of trying to prove. This is a rather unscientific definition, but there you have it. Together, these are complementary. I said complementary, maybe it's unreadable, but you know what I'm talking about. Meaning, they exist together. The null and alternate hypothesis encompass the entire realm of possibilities. So, what are we talking about here? I'm sort of talking in generalities. Generally speaking, the null hypothesis will be something like the average for the population, or the proportion, the overall proportion in the population is a certain value. And the alternate hypothesis will be it's not that value. So oftentimes, you might be testing a claim, or seeing if something has changed from, the way a value has changed from what it used to be. You might it's often sort of this idea that we have an assumption, something that is sort of an agreed upon truth, or a general assumption, or that would be the default way of thinking about it. That's the null hypothesis, and it usually means the population has an average, or the population has a certain proportion. And the alternate hypothesis is it's different. It's not that. It's something else. You might also, that's one way of doing a null hypothesis. You might also have a situation where you say, you know what, the null hypothesis is that the population has this trait that it's more than, it's that or greater. It's a certain value or greater, or it's a certain value or less. In which case the alternate hypothesis would be, no, it's actually the opposite. So, if we had the null hypothesis was u is greater than or equal to 15, the alternate hypothesis would say u is less than 15, for example. The thing about the null and alternate hypothesis is this. The whole thing we're doing is we have an assumption about the population. That's our null hypothesis. And we're trying to sort of disprove it. And so we've taken a sample. And we want to know whether or not that we have enough evidence to disprove the null hypothesis. And the burden of proof is really on the alternate hypothesis. You're only going to reject the null hypothesis and accept the alternate hypothesis if you have really a preponderance of evidence. So usually, sort of typical is that you're at least 95% sure that the alternate hypothesis is true, in which case you reject the null hypothesis. Usually, 95%. Occasionally you go down to 90%, and a lot of research, it's going to be you want to be even more confident than 95%, so you might want to be 99% confident. If you fail to reach the required threshold of confidence, and you don't reject the null hypothesis, meaning you don't have quite enough evidence to accept the alternate hypothesis, it doesn't actually mean that you accept the null hypothesis. It just means that you don't reject it. This is a funny little thing. If you have enough evidence to prove the alternate hypothesis, then you accept the alternate hypothesis. And that might be that, no, the population mean is not 15, in which case you will accept the alternate hypothesis. But if you don't have enough evidence, if you don't reach that, say, 95% confidence threshold, it doesn't mean you accept the null hypothesis. You never really accept the null hypothesis. You just don't disprove it. You don't accept the alternate hypothesis. You just say, well, we don't have enough evidence. We don't know. All right. So let's take a look at an example here to illustrate these concepts, because we've been talking in a lot of generalities. Okay, a fast food restaurant chain advertises that their burgers are, man, so many typos in these, are 12 ounces. They therefore require their suppliers of beef to send them 12-ounce raw patties, no larger and no smaller. The restaurant chain decides to test the patties from their main supplier. They want to be 99% sure of their results, so they test 10,000 patties and find that the patties average 11.99 ounces with a standard deviation of 0.35 ounces. Will the restaurant chain be complaining to their main supplier? Okay, so first thing we need to do is set up a null and alternate hypothesis. In this case, the null hypothesis is that the overall population of beef patties being supplied by the supplier have an average weight of 12 ounces, right? That's kind of the default. That's the assumed. We assume that the main supplier is doing right by us and that their patties are 12 ounces. The alternate hypothesis is that population of patties being supplied is not equal to 12 ounces. So they might be larger or they might be smaller. We don't want them to be larger or smaller. So they require their suppliers of beef to send them 12-ounce raw patties, no larger or smaller. So that's our null and alternate hypotheses. Now here's how I like to do it. I like to figure out the number of standard deviations we can be away from the mean that would cause us to say, yeah, with 99% confidence, we will reject that null hypothesis. So let's take a look at this. I'm going to draw out a curve. And so our middle value is 12 ounces. If we end up since we need, so we're going to be 99% confident. These values out here, these are going to be 0.5%. And all of this part in the middle, 99%, this is the don't reject area, right? We don't know the number of standard deviations that encompasses, but we can figure that out pretty quick by looking up on our z-table. Why our z-table? We're not given, let's just take a moment here. We're not actually given the standard deviation for the population. Why wouldn't we be using a t-table? Well, the answer to that is this. We're testing 10,000 patties. That's a really big sample size. Huge sample sizes like that, t-table and z-table are basically the exact same thing. And so we're going to just go ahead and use the z-table. It would make almost no difference if we use the t-table, so what the heck. But yes, if there was a t-table that had degrees of freedom of 9,999, we might use that, but like I said, it would give us the same values. So this is the area, if we're within this number of standard deviations, we're going to not reject. If we're this many standard deviations more or this many standard deviations less, we will reject. And let's look up how many standard deviations that is. We're dealing with an alpha divided by 2, and our alpha was 1%, so we're looking up 0.005 on that z-table. And actually, since we know that the sample average was smaller than 12 ounces, I'm going to go ahead and start on the negative end. So I'm looking for 0.005. It's somewhere in between negative 2.57 and negative 2.58, so I'm going to call it negative 2.575. That's this right here. So, if we are more than 2.575 standard deviations away from the mean, and then we know it's, if we are, it's going to be to the left. We're going to be somewhere out here. If we're more than negative 2.575 from the mean, then we're going to go ahead and reject the null hypothesis and accept the alternate hypothesis. Now it's just a matter of using our standard equation for dealing with sampling. So let's do that. Our X bar is 11.99. That was our observation from the sample of 10,000 patties. Our N is 10,000. Our S is going to be equal, and again, I said this is interchangeable. Our standard deviation for the sample, I'm going to call it what it is, which is the standard deviation for the sample, but it's a big enough sample that it's going to be the same thing pretty much for the population, is 0.35 ounces. So let's go ahead and use that. We say, oh, and by the way, our assumption here is that mu is equal to 12 ounces. So we say 11.99 minus 12 divided by 0.35 divided by square root of 10,000, also well known to be 100. And that gives us negative 2.857. All right, so what does this tell us? What does this tell us? Negative 2.587, that's to the left of negative 2.575. Let me see if I can sort of draw this. And it's going to be somewhere like right around there. It's more than 2.575 standard deviations from the mean. Therefore, with 99% confidence, we can say, yeah, we don't think the patties that you're giving us are 12 ounces. We actually think they're a little bit smaller. But the main thing here is we're accepting the null hypothesis, which is that the patties that they're giving us are not 12 ounces. So would we complain to this main supplier? Well, based on this evidence, yeah. Two things I want to point out here. Number one is this large sample size. When you're dealing with very large sample sizes, little tiny differences can make a big difference. You might have looked at this and said, I'm pretty sure that 11.99, that's really close to 12, so I think we're going to be okay here. But in fact, because we dealt with such a large sample size, we actually would have expected it to be closer to 12. This is a pitfall, though. In real life, in terms of practical, actual practical application, which is that you might have been 0.01 off just in terms of your scale or your measurement. There's a lot more likely reasons for that difference. Maybe just there's the way you guys are measuring it. Maybe it's losing a little bit of moisture in the shipping process. Who knows? There's a lot more sort of reasonable explanations than that your supplier is trying to cheat you, especially when you're dealing with this small of a difference. And the reason that this tiny difference became significant was because of the large sample size. Large sample sizes are usually good, but it can lead to you getting significance, even at the 99% level, very, very, very often. So it's worth thinking about that and taking those results maybe with a grain of salt. So let's look at another example. Here we have the same fast food restaurant. They advertise a new contest for which they claim 1 in 5 will win. And there's a consumer protection group, and they decide to test this claim by sampling 200 purchases. They want to be 99% sure that the contest claim is false before they bring a lawsuit against the chain. So they're testing this claim that 1 in 5 will win. They do so by making 200 purchases, and they want to see how many winners they have from those 200 purchases. If their sample provides only 29 winners, do they have enough evidence to bring a lawsuit at their desired level of confidence? All right, so they got 29 winners out of 200. First of all, let's set this thing up. We have a null hypothesis, which is going to be the assumption, which is basically that 1 in 5 will win. Except this is a little funny, because it's not exactly like the last one. Last time we cared. We wanted those patties to be exactly 12 ounces. But let's say more than 1 in 5 will win, right? What if 1 in 4 actually end up winning? Is anyone going to have a problem with that? Can the consumer protection group bring a lawsuit? No. No, that'll be just fine. Everyone will be happy. Maybe not the fast food chain, but they really care. Their assumption here, that the null hypothesis, is that P, the probability of winning, is greater than or equal to 0.2. In other words, if the fast food restaurant chain, if they're not liars, the probability of winning is going to be 1 in 5, 0.2, or higher. The alternate hypothesis, therefore, since these have to be complements of each other, is going to be p is less than 0.2. And this is where the burden of proof is. We need to try to prove that p is less than 0.2. So this is what's known as a one-tailed test. When we really just want to know whether, if the alternate hypothesis is just that the average, the proportion, is not what is claimed by the null hypothesis, then we have something called a two-tailed test. And that's what we saw here, two tails, here and here. But this is a one-tailed test, and it's going to look something like this. We really just want to know, this is p equals 0.2, and we're interested in what's over here. How many standard deviations are we going to be, how many standard deviations to the left, only to the left of the mean do we need to be to say we reject this claim by the fast food chain? We think that, in fact, we have enough evidence to say with 99% confidence that, in fact, less than 1 in 5 are winning. How many standard deviations to the left of the mean or left of the assumed mean do we have to be in order to say that ain't really the mean? Okay, so let's look that up on our z table, right? We need to know, we have z, and this, and since it's just our alpha here is 0.01, and it's a one-tailed test. So this over here is just 0.01. So let's look that up on the z table. It's like, I'm going to call it negative 2.33. Yeah, it's somewhere in between there, but a little bit closer to 2.33 than negative 2.32. So we'll call it negative 2.33. That's our threshold. If we get more than negative 2.33 standard deviations to the left, then we're going to reject the null hypothesis with 99% confidence and we'll bring a lawsuit. If we're anywhere in here or over here, then we cannot reject the null hypothesis and we'll just go on our merry way. So let's look at our proportion that we got from the sample. Let's set this thing up. So 29 divided by 200 is going to be equal to 0.145. So that is our sample proportion, equals 0.145. And we got everything else we need, right? So we're going to say 0.145 minus 0.2 divided by, and again, you know, you've seen this before, the equation for the standard deviation of a proportion is going to be p times 1 minus p divided by n, square root of the whole thing. So in this case, our p is 0.2, so we say 0.2 times 1 minus 0.2, also known as 0.8, divided by 200. Square root of all of that. And that gives us negative 1.945. That's going to be somewhere right around there. So, do we have enough evidence to reject the null hypothesis? No. We cannot say that the claim of the fast food chain is false. We cannot say that definitively, or we cannot say with 99% confidence that less than 1 in 5 will win. Now, I want to point something important out here. There's actually a pretty decent amount of evidence. I mean, 29, we were expecting to get 40 winners or something around there, and we got 29. That's pretty low. And negative 1.945 actually has a pretty, it's fairly significant. Let's actually look that up. Negative 1.945. It's, you know, it's about, I mean, it's better than 97% confident. If we had set our threshold at 95% confidence, we would have been in the money. but actually, since we said 99% confidence, we weren't able to get there. And here's the point I want to make. Just because we didn't reject the null hypothesis does not mean that the null hypothesis is true. It just means we weren't able to reject it at our desired confidence level. So therefore, we can say we're not ready to make a claim in court that our alternate hypothesis is true. But we're certainly not accepting the null hypothesis. We never really accept the null hypothesis. We just try to disprove it, and we weren't able to do that to our level of satisfaction. So this can lead to one sort of error. There are actually two kinds of errors you can make in hypothesis testing. The type 1 error is when we reject the null hypothesis when it's true. That can only happen if you end up rejecting the null hypothesis and accepting the alternate hypothesis. Let me actually make a little bit of room here because I want to illustrate something. Not exactly what I wanted to do. See if I can just get part of this. All right, well, I'm not going to worry about it. We'll move everything over to the left, and I'll give myself a little bit of room. The chance of this happening is alpha. It's also known as the significance level. Or 1 minus the confidence. So, this might have happened in our first example. In our first example, we did reject the null hypothesis, and we did so with 99% confidence. Therefore, the chance of us having made a type 1 error was basically 1%. We said, yeah, you know, we're pretty sure. We're not 100% sure. You're never 100% sure. So the possibility of us having rejected the null hypothesis when in fact the null hypothesis was true was 1%. Type 2 error occurs when we fail to reject the null hypothesis when the null hypothesis is, in fact, false. So that certainly might have happened here in our second example. We needed to be 99% sure. We had pretty compelling evidence that the null hypothesis was true, but it didn't reach our 99% threshold of confidence. Therefore, we did not reject the null hypothesis. However, it certainly might have been false. So there's a pretty decent chance we committed type 2 error here. Funny thing about type 2 error is it's kind of hard to measure. So it's not as straightforward as committing type 1 error when you know you've rejected the null hypothesis and you've known your significance level and you've sort of made your bed and you're just like, I'm going with this. I know there's a possibility, a certain possibility of having committed type 1 error. With type 2 error, it's a little bit trickier. You will know that it's a possibility when you don't reject the null hypothesis, but you won't exactly know how likely it is that you made type 2 error. One more note about type 1 error. We're going to talk about p-values a little bit later. This is a little bit, especially the 1 minus your confidence interval, is a little bit, it's not exactly accurate. When we get to p-values, it'll be much more clear exactly what the probability of making type 1 error. But this is a close approximation, except I may have misspelled this. No, we're okay. All right, so let's move on to another example. A factory has been using an old machine that produces 32 parts per hour. A new machine is supposed to be faster, but the factory supervisor wants to be sure. So, being a conscientious statistician, the supervisor tests the new machine over a 36-hour period, during which time it produces 1,197 parts with a standard deviation of 3 parts per hour. With these results, how confident can the supervisor be that the new machine is faster? So this is sort of an interesting question. Oftentimes what you'll see is researchers will set a certain confidence threshold. I want to be this sure. But in this case, we're actually asking what's the confidence level that we get from using these results. Okay, so let's start working through this, and you're going to see that we don't actually need to have a pre-established confidence interval. in order to work these problems. So we're going to start off by defining our null and alternate hypotheses. In this case, our null hypothesis is that the machine is just as fast as the old machines, and that the average is 32, or maybe it's even slower. So let's just make that assumption. The assumption is that it is not faster than 32 parts per hour. So we'll say less than or equal to 32 parts per hour. I'm just going to abbreviate that. And the alternate hypothesis is that the average of this machine is in fact greater than 32 parts per hour. All right, so let's work out everything else we know. Well, we know the average that we got from this sample is, we worked the new machine for 36 hours, and we got 1,197 parts. So if we divide that out, we get 33.25 parts per hour. And the sample standard deviation is 3. The n is equal to 36. And the degrees of freedom based on that n is going to be 35. N minus 1. All right, so we can start working through this thing. And we're using a t-test because we got the standard deviation from our sample. It wasn't sort of somehow given to us from the population. We got the 3 parts per hour standard deviation from our sample, and this is not a gigantic test. We only have an n of 36, so we need to use that t-table instead of the z-table. We need to be conservative in our estimates. So let's put this together. We have x bar minus mu, so we have 33.25 minus 32. By the way, you know I like to draw these out, so let's do that real quick. This is what we actually measured here is 33.25. We want to figure out how many standard deviations. How many standard deviations above 32 is 33.25? And knowing how many standard deviations will give us the confidence level that we are looking for. So on the denominator, we have 3 divided by square root of 36. And all of this gives us 2.5. All right, so that tells us we are 2.5 standard deviations above the mean. Now we need to look up our t-table look up in our t-table with the degrees of freedom 35, 2.5 standard deviations, what kind of significance level does that give us? All right, so let's go to our t-table. All right, so first of all, let's get to our degrees of freedom, which is 35. And we're looking for 2.5 standard deviations. Now, this is as close as we're going to get. The t-table doesn't always give you exact numbers of standard deviations because we don't have an infinite number. We don't have an infinite number of columns. We don't have an infinite number of significant levels across the top. If we did, we could get exact standard deviations, but we don't. So 2.438 is about as close as we're going to get. And it's actually a little bit conservative since we're going to get a confidence level that's slightly below what it would be since this thing goes up. But let's find out what our confidence level is. Okay, it's 0.01. And this is a one-tailed test, right? So that means we can be a little bit more, actually, than 99% confident that we can reject our null hypothesis and accept an alternate hypothesis. So we are around 99% confident that the new machine is faster. So this is one thing you can do. You can actually start off with no preconceived notions about confidence intervals and just try to get to, just say, okay, what this really says is if the new machine actually operated at 32 parts per minute, if we took that 36-hour sample, the chance of us getting 33.25 as our average over that 36 hours is less than 1%. It's about 1%, but it's actually slightly less than 1%. That's what we call our p-value. is slightly less. I'm going to just call it about 1%. And the p-value can be translated into a certain confidence. So sort of 1 minus the p-value is your confidence in rejecting the null hypothesis. Confidence in rejecting the null hypothesis is 1 minus p-value. So in this example, research indicates that smokers who quit have an average weight gain of around 10 pounds 12 months after cessation, with a standard deviation of around 10 pounds. So a lot of variation in results for quitting smoking. But a year after quitting, average weight gain is 10 pounds, standard deviation of 10 pounds. A new quitting intervention is being tested by a medical company which they believe may also change the tendency to gain weight. It doesn't say how they believe it's going to change. They believe it's going to change the tendency to gain weight. They test their new intervention on 400 smokers who are trying to quit, and they find that they gained only 9.35 pounds on average. What is the significance level for this test? What is the p-value for this test? And that can be translated to how confident can we say that this actually does lead to a change in weight gain following treatment. So what is our null hypothesis? Our null hypothesis is that average weight gain is equal, for this new intervention, is 10 pounds, because that's the standard. Our alternate hypothesis is that the average weight gain is not 10 pounds. Now, some of you might have said, you know, the null hypothesis is that the weight gain is 10 pounds or greater, and the alternate hypothesis is that the weight gain would be less than 10 pounds. But actually, especially true with medicine, we don't usually make those assumptions. We usually say, you know what, we just want to know, is it different than what we expect? Because, you know, maybe the weight gain would be more, in which case that would be significant as well. So we're just going to say it has a different effect than the standard treatments. So let's go ahead and set this thing up. We have an X bar from our sample, a measured average from our sample of 9.35 pounds. The assumption is 10 pounds. And the standard deviation the standard deviation overall is 10 pounds divided by the square root of our sample size, which is 400. So I didn't write everything down this time. I figure you guys are sick of seeing me write it all out. But our n is 400. Square root of 400 is going to be 20. So we can calculate this whole thing out, and we get negative 1.3. Before I forget, let's actually draw this curve out. Let's draw what we're trying to figure out. All right. This is a two-tailed test, right? We're interested in knowing if there's a difference from 10 pounds. So we're going to be interested in both this, whether it's less than 10 pounds, and whether it's greater than 10 pounds, right? And where does this z-value land us? Well, this is negative 1.3 standard deviations. So this is our x bar, and that happens to be negative 1.3 standard deviations, a z-value of negative 1.3. What does that give us? Let's go to our z-table. Negative 1.30 is 0.0968. So just for the sake of making this a little bit easier, I'm going to call this 10%. It's close enough. Okay, so that's 10%. So if, in fact, the real value for the real average weight gain for this new intervention was 10 pounds, there'd be only a 10% chance we'd see that value, or we'd see the value of 9.35 in our sample of 400 or lower. But we also have this possibility out here. In other words, there is if we add this, because these are symmetrical, what this tells us is that there's a 20% chance that we would see that we would end up more than 1.3 standard deviations from the mean. Therefore, when we say what's our p-value here, it's actually 10%, and again this is a little bit of an estimate, plus 10%. So our p-value here is going to be 0.2. And our confidence in saying, oh yeah, there is a difference in terms of the weight gain, is going to be 1 minus 0.2, which is equal to 80%. So we can be 80% confident there's a difference in weight gain for this new intervention. Is that enough to make the claim publicly? Probably not. So if you have 80% confidence, it's likely that you're going to say, yeah, maybe we need to do more testing with a larger sample, but it's probably not enough to be sure enough to make the claim publicly. All right. So what is all of this, in terms of hypothesis testing, what are the key takeaways here? Well, hypothesis testing is all about, first of all, identifying your null and your alternate hypothesis. Remember that the null hypothesis is going to be the default. It's this thing that you've assumed, and what you're trying to do is you're trying to gather enough evidence to say whether you can reject the null hypothesis. The burden of proof is always going to be on the alternate hypothesis, meaning you have to have really good confidence, usually around 95% or more, in order to reject the null hypothesis and accept the alternate hypothesis. If you don't reject the null hypothesis, you're not necessarily accepting it, you're just saying don't have enough evidence to reject it. Again, I want to emphasize type 1 and type 2 errors. Type 1 error occurs when you reject the null hypothesis, when the null hypothesis is in fact true. That's sort of the complement to your confidence. So it's 1 minus your confidence level, or actually it's more accurately, it's 1 minus your p-value that you got from your sample. Type 2 error happens when you fail to reject the null hypothesis when the null hypothesis is false. The only other thing to it is identifying whether you're dealing with a one-tailed test or a two-tailed test. So, just to draw these out, in a one-tailed test, you're just dealing with this, and this is your alpha. In a two-tailed test, you're dealing with both sides. And so each of these is going to be alpha divided by 2. So, for instance, if you're looking for 95% confidence in a one-tailed test, you're going to look up the z-value for 0.05 or 0.95, whichever you prefer, whichever side you're dealing with. But in this case, you'd be looking at the z-value for 0.05 based on the way I drew this. Of course, I could have switched sides on this thing. It could have been over here. But in the two-tailed test, if you're looking at 95% confidence, you're going to look up the z-value for 0.025 and its corresponding z-value on the positive side would be for 0.975. So those are the only real rules. Hypothesis testing doesn't include any new math that you don't already know. It's really about coming up with a solid null hypothesis, getting the burden of proof to say whether or not you can reject the null hypothesis, and then of course identifying things like the types of errors that you might make and whether it's a one-tailed or a two-tailed test.